Binomial heaps is a kind of mergeable heaps. We call this as a mergeable heaps. So this is a new data structure that is called mergeable heaps. So this data structure can be implemented using min heaps, and that can be implemented by the max heap, but the time complexity taken by the min heap and max heap for this type of data structure is more than binomial heaps. So binomial heap is nothing but a data structure known as a mergeable heaps which support 5 operations. First is insert make heap. Sorry, make heap. This operation will create a new heap containing no element. Second operation is insert. So insert, if we have existing heap H and we need to insert an element with information X. So this insert procedure will insert node X whose key field has already been filled in into the heap existing heap H. Okay, so the node X with some key is inserted into the heap H. Next is minimum operation. This minimum operation on any heap H returns a pointer to the node in the heap H whose key is the minimum. Okay, now fourth is extract. So I consider here the min heap in order to implement the mergeable heap using binomial heaps. So I follow the extract min property because the min heap is considered here. So the extract min, what it does, it deletes the node from the heap whose keys is minimum, and it will return a pointer to the node. Okay, then next and final operation is, which is most important operation by this binomial heap, which is union. So the union operation will performed on two heaps h1 and h2. So what it does, it will create a new heap that contains all the node from h1 and h2, and it will free the memory occupied by this h1 and h2 individually. So this union operation will free the memory of h1 and h2, and it will combine the nodes taken by these two into a new heap. Okay, so these are the main 5 operations that is performed by mergeable heap data structure. Now in order to implement this type of data structure, we are using binomial heaps. So inspect of, instead of these 5 operation, we also have two main other operations for the for this data structure. So two other operations are decrease key operation. So if you want to decrease a value of any element in the heap, then we can call this procedure decrease key on heap H with X node and the decreased value K. Other is delete. If you want to delete any node from the heap, then we call this procedure, so it will delete node X from the heap H. Okay, so if we apply this union operation on the ordinary binary heaps, whether it is a max heap or a min heap, then this binary operation will take generally order of log n time, sorry, order of n time, because it will combine uh, two or more elements from the heaps. Okay, so the binary heaps, if we consider the binary heaps or the ordered array, ordered list, or any unordered array, the union operation will generally take order of n time in order to combine these two type of data structures. Okay, So the binomial heap union will reduce this time to order of log n. That's why we are using the binomial heaps in order to implement the mergeable heap property. Okay, so this is the power of the binomial heap. Now let's understand the binomial heap in more detail. So binomial heap is nothing but a collection of binomial trees. So first thing we have to note it down is binomial heap will is a collection of binomial trees. This is the first point. And now we need to know what is a binomial tree. So binomial tree is a order tree which is defined recursively. Okay, so binomial tree is a order tree which is defined recursively. So recursively in the sense, suppose we need to define a binomial tree bk. So for example, if you define binomial tree b0, then it will contain only one node. So for binomial tree b1, it will contain a node, two b no node. So it is a b0 node, and at the left of it child is also a b0 node. So it will be a collection of two b0 nodes. Similarly, if you want to draw a binomial tree with 2, the value of k is 2, then it is a collection of two b1s. So it is a b1 dot, it is also a b1. So collection of two b1s are there. So it is a ordered tree which is defined recursively. Okay, so the root of the root of the one is the leftmost child of the other. Okay, so the common properties of binomial tree are: first is, in any binomial tree there are 2 to the power k nodes. For example, if I say that for a binomial tree b0 how many nodes are there, so it will contain only one node, 2 to the power 0. Similarly, for binomial tree b1 how many nodes are there, it will contain two nodes. You can verify from here. For binomial tree b2 how many nodes are there, 2 to the power 2, it means it will contain 4 nodes, and so on. So this is the first property, every binomial tree will contain 2 to the power k nodes. Second is, the height of the tree of any binomial tree is nothing but k. So the height of 0th binomial tree b0 is 0. The height of b1 is 1. The height of b2 is 2. Third property is, the number of nodes, or we can say the maximum number of nodes at depth I is given by kci, which is equal to factorial k upon factorial I into k minus 1 factorial, sorry, it is k minus 1 factorial. Okay, so at depth I how many nodes are there, factorial k upon factorial I into factorial k minus I. So you can verify it. So suppose if you want to calculate the number of nodes at in b2, so if you want to calculate the number of nodes in b2, so uh, the number of nodes at depth in b2, so you can write it like the number of nodes at b2 at depth 1. Okay, so the number of node in b2 at depth 1, so this is your depth 1. How many nodes are there? So here it is 2, so it is nothing but 2c1 or 2c1, the value is 2. Okay, so similarly you can verify for others. The fourth property is the degree or maximum degree of the binomial tree. The maximum degree of binomial tree is equal to the degree of root. So root have the maximum degree in the binomial tree. Okay, and these are, so these four properties are followed by every binomial tree, and there are some corollaries or there are some lemmas which is also important to know. And the you can say that lemma 1 is the maximum degree, the maximum degree of any n-node binomial tree is of any n-node binomial tree is nothing but log n. So any binomial tree can have the maximum degree as log n. Okay. Now, so this is about the binomial trees. Now, what is binomial heap? It is a collection of binomial trees. So let's see the definition of binomial heap. So as we see that binomial heap is a collection of binomial trees with the following properties. First is every binomial heap, in every binomial heap, each binomial tree, each binomial tree in heap H obeys the min heap property. Min heap property. What min heap property says that every parent value or parent information is always lesser than the child information. This is the first property. Second is for any non-negative integer k, for any non-negative integer k, there is at most one binomial tree in H with degree k. What this property emphasizes that in any binomial heap there are no more than one binomial trees available for the same degree. So for any non-negative integer k, there is at most one binomial tree in H with the degree k. We do not have more than one binomial tree with the same degree k. Or this point can also concludes that your H consists of at most log n plus 1 binomial trees. So we cannot have more than that number of binomial trees log n plus 1. Okay, we just prove it in here. So the first point says that we have the root have the smallest value in your heap. The root list have the smallest value in your binomial tree. So the root list in binomial heap always have the smallest value in the each tree. And for any non-negative integer k, there is at most one binomial tree in heap H with the degree k. So this point says that every binomial heap contains the binomial tree uh, with the uh, unique degree. Means every binomial tree have a unique degree. There are no two binomial trees are possible with the same degree. Okay, so by that point we can say that for any binomial heap there may be at most log n plus 1 binomial trees. So why it is like that? Why it is like that? So suppose we have a n node binomial tree, n node binomial tree. So suppose for example the n node is 15. So the binary representation for the 15 is nothing but 1 1 1 and 1. Okay, so let's take another example. Suppose the integer representation is 13 and the binary representation of 13 is 1 0 1 1 0 0 1. So in that case, I can say that in the binomial heap with n node, we can have only b0, b2 and b3 binomial trees. We cannot have b1 binomial tree. Okay, so uh, because the integer representation of any number can take at most log n plus 1 bits. Log n plus 1, how I can say log n plus 1? It will contain b0 to b log n number of bits. So the total number of bits is log n plus 1 because it starts from the b node. Okay, so the integer value of this same can be calculated at sigma I is equal to 0 to log n bi, the index value, into 2 to the power I. So by that formula, if I feed this string into this formula, then I can got the integer value 13. Okay, so this is all about the binary system, number system. So by the binary number system, we can see that this type of the integer can be represented in log n plus 1 bit. Similarly, for n node binomial heap, we can have at most log n plus 1 number of binomial trees. And if you want to find out that which binomial tree is available, then represent the number into the binary and check where the b of I is equal to 1. So those bits on which b of I is equal to 1 will be included in the binomial heap. Okay, so the 13 node binomial heap can be look like this. We have a node with degree 0, we have a node with degree 2, and we have a node with degree 3. So some 3 children are attached with this. Okay, so this is the example of your 13 node binomial heap. Here head is the pointer. Okay, so this is all about the definition of binomial heap. Now how you can represent this binomial heap in the memory. So the representation of binomial heap. So next is representation of a binomial heap. So how can we represent? So if you want to represent a binomial heap in a memory, then it will contain the following information. So for the representation, the node structure would be having the 3 pointers. So uh, there are 2 types of nodes in binomial tree. Uh, one is the root node and other is, if it is not a root, it means it is a child. Okay, so for those we have different type of representation. So if your node is a child, it means it will look like this. Okay, so what it contain? It will contain the information or the key value. What is the degree of this node? Which so these two integer fields are there. One is a parent, one is a pointer of, so if it is a node x, then what is a parent of x? Then it is a pointer which is pointing to the parent of this node. Other pointer is a child of x, the leftmost pointer is child of x, and other pointer is a sibling of x, sibling of x. So this will point to the sibling of this node x. So if it is a suppose so this is the node structure. So if you consider this node as a root, then parent of x would be nil. If this is a leaf node, then child of x would be nil. And if it is the rightmost node of the tree, then the sibling of x would be nil. So based on the position where this node appears, the pointer value will be initialized. Okay, so one more point is that which is important. So this is all about the representation. So the point is, if we have a n node binomial heap, then we can say that the degree of roots are strictly increases as we traverse the root list. So the root list is arranged in the increasing order of degree of the nodes. Okay, so by this property we can say that if any node x is a root, then the degree of sibling of x, if it is a root, then the degree of sibling of x is always greater than degree of x. So this point says that your root list always like this: the first node with degree 0, the second node always have the greater degree than this node, and the third node is always greater than degree than this node. So the root list are strictly in the increasing order of as we traverse the root list. Okay, so by this property, if x is root, then if this is x, then degree of sibling of x means degree of this node is always greater than degree of x. Okay, and if x is not a root, then I can say that degree of sibling of x is equal to degree of x minus 1. So suppose x is not a root, means x is a child. So the degree of sibling of x means this one is nothing but degree of this. The degree of this is 1 and degree of this is equal to 0, means 0 is equal to 1 minus 1. So degree of sibling of x means 0 is equal to degree of x minus 1 if it is not a root. So these property, so this is a very important property in case of binomial heaps. In the root list, the nodes are arranged in the increasing order of a degree. Okay, so these are all about the properties of binomial heap. Now we perform some of the operation on the binomial heap. So let's start with the operation of a binomial heap. So I just write here operations on a binomial heap. So operations. So the first operation is finding the create a new binomial heap. So create heap. So this operation will create an empty heap and assign a pointer head of h to nil. Okay, so this will take order of one time. Then second operation is, this is the first operation. Second operation is finding minimum element. So in order to find the minimum element in heap, we have to check the root list only, because at the root list is the minimum one. So we have at most how many number of nodes in the root list? Log n plus 1 nodes in the root list. So the time complexity of this one is nothing but order of log n. So let's say this is the given binomial heap with the 25, here it is a 12 and 18, and then it is 6 with value 29, 14 and 8. Okay, then this value is 38 and this value is 17, then here is 11 and here is 27. Suppose this is the heap, and here is a head pointer, head of h. Okay, so initially the find the minimum algorithm says that we have pointer x which start from the head of h, and we will traverse the root list in order to find the minimum element. Okay, so how we traverse, we just take an min and auxiliary uh, variable in which we put the infinitive. So we have to execute while my x is not equal to nil, and we need to check whether the key of x is less than the min. So at first time key of x is less than the min, yes, we replace the min with the key of x and then assign a pointer to this. So suppose the pointer which is assigned is y. Again we update the value of x to the next, and then value of x is equal to sibling of x, then check whether the key of x is equal to less than min, yes, so we update 1 here and uh, update the value of y also. So y is now pointing to it. Now x is pointing to sibling of x, so this will be going here x. So now check whether key of x is less than 1. No, it is not less than 1. So we do not update the y as well as we do not update the min, but we update the x. So x will now point here, which is nothing but nil. When x is equal to nil, the processor stops and it will return the y. So the pointer of y is now pointing to the minimum element in the root list. So this procedure will take order of log n time in worst case, where we have to traverse the whole root list. Okay, now the next operation is uniting two binomial heaps. So the union operation of the two binomial heaps. So this procedure we will discuss in the next video tutorial. Thank you very much.